Alright, this is a tutorial on temperature and heat. So if we look at a couple of problems here, let's look at some basic temperature conversions. First, we're going to convert 105 degrees Fahrenheit to Celsius and Kelvin, and then we'll start with Celsius and go to Fahrenheit and Kelvin. So what are our formulas for the conversion? We got degrees Fahrenheit equals 1.8 times the temperature in degrees Celsius plus 32. The 1.8 is because there's 180 degrees between freezing and boiling of water on the Fahrenheit scale and 100 on the Celsius scale. Because if we establish a scale where this is the boiling point up here, this is the freezing point down there, it's 32 degrees Fahrenheit, 212 degrees Fahrenheit for the boiling point, then 0 degrees Celsius, 100 degrees Celsius. So this is 100 degrees, this is 180 degrees, so 180 divided by 100 is 1.8. You could do the 9/5, but I find that a lot of people find the fractions confusing. And then if you want to get Celsius, it's just an algebraic rearrangement of that, so it's Fahrenheit minus 32 divided by 1.8. And then once you have Celsius, Kelvin is degrees Celsius plus 273. So let's work that. So if we got degrees Celsius from Fahrenheit, so we got 105 degrees Fahrenheit minus 32 divided by 1.8. And so running that through on our calculator, we got 105 minus 32. Take that quantity divided by 1.8, and you get about 41 degrees Celsius. It's good to think about whether a temperature is hot or cold. 41 degrees Celsius is actually pretty warm. 41 degrees Fahrenheit is getting to be a little cool. Yeah, this is part A. And now we want the Kelvin, so Kelvin is going to equal 41 degrees Celsius plus 273. We're going to do that addition, and you're going to get essentially 314 Kelvin. So that would be part A. Part B, we're going to convert Celsius to Fahrenheit. Now, 25 degrees Celsius is what in a lot of scientific measurements is considered to be room temperature, which is why we picked that one for this example. So degrees Fahrenheit is equal to 1.8 times 25 degrees Celsius plus 32. That's going to equal 77 degrees Fahrenheit. And if you run that through on your calculator, that is an even conversion, no decimals or anything, which is probably why they picked that to be the temperature. Because for most people, that's probably a bit warm for a room. Regardless, the Kelvin then, we're going to go back to the Celsius. Don't do it from the Fahrenheit or it'll be messed up. Plus 273, and that'll be 298 Kelvin. And so remember that that's what's considered room temperature for a lot of scientific measurements. All right, so that's temperature. What about heat? And so we want the specific heat capacity of ice is 0.5 calories per gram degree Celsius. Don't know what that character is there. Just ignore that. How much heat would it have to be added to 200 grams of ice initially at negative 10 degrees Celsius to raise the ice to the melting point and to completely melt the ice? So if we just want to raise the temperature of the ice to the melting point, we're going to use Q equals the mass times the specific heat times the change in the temperature. So this is my C. We're going from a -10 to 0, because that's the melting point of water. And then we've got the mass. So Q is equal to 200 grams times the 0.5 calories per gram degree Celsius. And then we had to raise the temperature 10 degrees, so it's 10 degrees Celsius. So the degrees Celsius cancel, the grams cancel, and we're left with calories. So 200 times 0.5 times 10 is equal to 1,000 calories. And so that's the answer to A. We raise the temperature up to the melting point, but now to completely melt the ice, we need to add in the latent heat of fusion. So Q is equal to the mass times the latent heat of fusion. That is the amount to actually melt the ice. And you can look these values up in your textbook, because there's one for the melting of the ice and one for the boiling of the water. Make sure you use the correct one. But 200 grams of ice, and then that's 80 calories per gram. And that's a constant, and it should be in your notes. So 200 times 80 would be 16,000 calories. But that's just the melting of the ice. And so the total for the raising of the temperature and the melting of the ice would just be the two values together. And so that would be the total amount for the raising and the melting. This would be the amount for the raising of the temperature, this would be the amount for the melting, and this would be the whole thing. Now, what about internal energy? Internal energy is given by U, so the change in the internal energy is going to be equal to the heat minus the work. Now, what about sign conventions? If this represents our system, if heat is going into the system, it's a positive value. But if work is being performed on the system, it's negative. Because positive work would be useful work that we could use for some process. So we'd want work to be coming out of the system so that we could use it. And then that's positive. And it naturally falls out of the mathematics that way, if you actually study the physics of it all. But it's heat minus work. So energy going into the system is still positive. We're just subtracting the work and flipping the sign. So what's the increase in internal energy? If we are transferring 400 calories of heat, 500 joules of work are done on the contents. So Q in this case, it's going into the system. It's being added to it by a hot plate. So it's going to be a positive 400 calories. Now the work is also going into the system. So it will be a negative 500 joules. Now notice this little asterisk down here says convert joules to calories per proceeding, because they gave you mix and match energy units, and we've got to fix that. Turns out there's 4.18 joules per 1 calorie, so we just need to do the conversion. And it's going to be about 120 calories. Now, and that's a negative, so we're going to keep that negative. So, change in internal energy is heat minus the work. And so it's going to be 400 calories minus 120 calories, or 400 plus 120 calories, or 520 calories of heat. So that was part A. Part B says, all right, if I do that, how much ice actually melts? Now we need to go back to our friend here. Assuming it's already at the freezing point, the amount of heat you would need to add is equal to the mass times the latent heat. What I want is the mass in this case, because we know how much ice melts. The mass is equal to the heat, or the amount of energy added to the system in this case, divided by the latent heat. And so we're going to use the 520 calories of energy added to the system, divided by the latent heat of 80 calories per gram. 520 divided by 80 is going to be 6.5 grams, because the calories are going to cancel. So this has been a brief tutorial on temperature and heat.